You know, it really helps if I unmute the mic. Uh, Pro streamer strats. Welcome to United Astronomy Clubs of New Jersey here in Jenny Jump State Park. So we do have a number of people who are just wandering down from getting parked. So in the effort to give them a little time to come down, get a bit settled, welcome to those not only here, but also joining us online. Because that's right, we do live stream these presentations to both YouTube and Twitch. So if you ever can't make it up here, always feel free to join us online, say hi in chat, and ask any questions you may have. You can check out a list of all our upcoming talks as well as information about all our member clubs through our website, uacnj.org. It's where you're going to find all of that information and more. And you can also check us out on our social media pages, our Facebook, our Instagram. We have a Discord server, all great places to get information on what events are coming up, or what talks, as well as ask questions. If you're into astrophotography, share those images. We do love to see those pictures and whatnot. So, you're not really here to hear me ramble on, but I do want to, for everyone here, give you the safety briefing. If you need to use the bathroom, that is the porta potty in the back to my left, your right. We also have a museum area and gift shop, which I will be manning after the presentation, because they still won't let me be in two places at once. That breaks the laws of physics, and unfortunately that's one of the laws of physics, or some of the laws that are really unbreakable, usually, as far as I know. In addition, when we go to leave, we are using our headlights because we also do not want to see anyone hurt or run over. I've been there, done that. 0 out of 10 would not recommend. It's also causes way too much paperwork. However, it is a state park. It does get dark, especially as it's going to be quite cloudy, it looks like, for right now. If we are using flashlights, do keep those pointed towards the ground. We don't need to be accidentally blinded by someone doing sick flashlight rave tricks. They're really impressive, but really blinding. We do have a number of volunteers. I do see one observatory open. Hopefully the clouds will clear off and we will get to stargaze after the presentation. But you are here for the presentation, which is The Life and Death of Stars by Walt Windish. Walt Windish has been interested in astronomy since he saw the Pleiades as a Boy Scout. He bought his first telescope in a date I can't read, but it looks like some time before I was born, and just in time to see Halley's Comet. Walt is the member of the North Jersey Astronomical Group and the Rockland Astronomy Club, and been volunteering here at Jenny Jump for over 20 years. And with that, I will leave it with Walt.
Thank you. Yes, I'm that old. Thanks for coming out. Boy, if you had to battle the same torrential downpours I did, you're definitely certified astro nuts. So thanks for coming down. Every year I'd like to do at least one talk on the life and death of stars. And this is the night. I'm going to talk about just some basic stargazing stuff, magnitude and that, some science principles. And then we're going to look at what happens to a star the size of the sun. What does that life look like? And then what does a life look like of a star that's 8+ times bigger than the sun? Ones that form black holes even. So let's just take a quick look at a couple of things astronomers think about when they're looking at stars. The first is apparent magnitude and absolute magnitude. Apparent magnitude is how bright a star looks in the sky. And that's really important for people who observe visually. Not as important as it used to be. Back when I was a kid, we didn't have GPSs, so we had to star hop. And the way we found objects in the sky was we looked at a bright star that we knew, And then we looked for the next brightest star, and we kept hopping over till we found the object that we need. Now, if you spend $2,000, $3,000 on a telescope, you got a GPS on it, you push the button, and it goes zzz, and it shows you exactly where it is. But apparent magnitude is still important because it helps us find the constellations, and it helps us find our way around the sky. It's like if you had a car that's close and a truck that's much further away, even if the truck has brighter headlights, the car is going to look like it has the brighter headlights because the apparent brightness of that car is brighter because it's closer to you. It's the same with stars. You see stars next to each other, one might be 100 light years further back than the brighter star that you see. So when astronomers do science, they want to know what the absolute magnitude is. And so what they have to do is they have to standardize the distance. They have to calculate the distance of each star and figure how bright would it be if it was 10 parsecs away, which is about 32 light years. And once it's standardized, no matter how far or close it is, you have an absolute magnitude. So you can see how absolutely bright that star is. And that's where science starts, because the absolute magnitude of a star tells us a lot of different things when we combine it with the spectrum. This is a list of some stars and their apparent magnitude. And this whole bit with magnitude started back about 2,000 years with Hipparchus. And some say even further back with Ptolemy. And they used to say the brightest star was a star of the first magnitude. And then the next brightest star would be a star of the second magnitude. When we get to the science age, where we actually have equipment that measures with precision I can't even imagine, as far as portions of light, we find that we have to adjust the first magnitude, and the brightest star is actually negative 1.5. So the smaller the number, the brighter the star, right? A first magnitude is brighter than a second magnitude, is brighter than a third magnitude. But Sirius is so bright that we have to call it a negative 1.5 magnitude because it just knocks it off the Richter scale. Venus at its brightest is negative 4.4. The moon is negative 12.5. And the sun is negative 26.8 magnitude. That's a really bright star because it's so close to us, right? If it was adjusted magnitude, it wouldn't be an average so-so star. Our vision can see, if we have dark skies, our vision can see to about magnitude 6.5. And so a lot of people use the star cluster, the Pleiades, which is a winter star cluster. And that has it has a 6.3, 6.4, 6.5. So you can look at how many stars you see in the Pleiades, can tell you how good the scene is and how good your eye is. You know, when you get to my age, you lose a few tenths of a magnitude just because your eyes get old. The binocular limit is about a magnitude 10. So if you use binoculars, you can see out to about magnitude 10. And the limit of the Hubble and the Keck is 30. I've heard the James Webb Space Telescope estimated at a magnitude of 35. But you know, if you point it even longer at an object, it can see further than that. At that point, it's just how long are you going to look at an object and how much light are you going to gather on those on the instrument panel, on the instruments. Another thing we need to think about is the electromagnetic spectrum. Our eyes only see a very small portion of the spectrum. This little tiny portion here is visible light, and that's all we can see. And actually, our eyes act like a camera that has a 1/30th shutter speed. So even though we can see visible light, if we look at something that has some color to it in the sky, it's not going to be bright enough, unless it's Jupiter or Saturn. It's not going to be bright enough for us to actually see those beautiful colors that we see when we see pictures of the Orion Nebula and all those nebula. You have to have expose a CCD or film for quite a while to gather enough light to see those colors. So sometimes when you look in the sky for the first time and you look at something you've seen pictures of and all colorful, it's a little disappointing because it looks more like a cloud or a wisp, very nebulous and without color, but still very cool. And if you come to my talk in September, I'm going to be talking about smart telescopes, And I'll tell you how you can get a telescope to capture that color right on your telephone for like $350. An amazing new breakthrough in telescopes. But that's not for tonight. Here we have infrared is to the left. It's a longer wavelength than visible. And the James Webb Space Telescope is entirely infrared in its imaging, because infrared can cut through dust and record heat better than visible light. So when you look at a Hubble picture in visible light, and then you look at a James Webb picture in infrared light, you have an awful lot of information, both about the dust that's blocking some objects and what lies behind it as far as the stars. We have microwaves, and radio waves are really stretched out very long. On the other side, we have ultraviolet, X-ray, and gamma rays. And we have instrumentation up in space to measure all of those different wavelengths. And some of the pictures you look at in a book are actually a combination of 2 or 3 of these different wavelengths from different telescopes that we have. And I'll point that out as we go along, because we're going to have the same situation. So what does that look like? Yeah, exactly. It's a bunch of dots. It's very random. If you have something that's, if you plot just random numbers along the X and Y axis, you're going to have something that looks pretty much like that. It doesn't really have any information. But there were 2 guys called Hertzsprung and Russell. They started plotting the absolute magnitude of stars against their color, their luminosity. And they came up with a chart that looks like this. And we see, this is very interesting. That's not a statistical chance. That's telling us something. And that line is actually called the main sequence. It's where most of the stars lay for most of their life. And since then, this looks like a dot matrix printer. And since then, we've gotten some really pretty ones. And colored, so we could see the hotter stars and the brighter stars are here. And then we come down. Here's our sun, right in the middle of the yellow stars. It's a very average star. Up here, down here, we have the white dwarfs, and here we have red giants. And we're going to see that as a star spends most of its life on the main sequence, just like our sun does, when it runs out of hydrogen, it moves off the sequence, because the luminosity and the color of the star changes with the size of the star, because the star starts to change. Just here's another chart. It just shows mass versus lifespan. So everything is geared towards the sun. So one mass is the sun. So one solar mass is the sun. So when you look here, we see that a star like ours, one mass, will live about 10 billion years. Something that's a brown dwarf, which is even cooler than our sun, could last for thousands of billions of years. We don't know yet, because our universe is not that old. But as you get bigger, the lifespan decreases quickly. You get to 3 solar masses, and you're already down to about 370 million years for a star. And the largest stars, 60 solar masses and above, which are very rare, they're only going to last a few million years. So the bigger the star, the hotter it burns, the more it burns through. Even though it's bigger and has more hydrogen, it's going to burn through that hydrogen faster, and it's going to have a shorter life. This is the same, just showing some, this is a HR diagram that also shows the lifespan on it. So you can see it, the higher up you get in here, the hotter the stars and the shorter the lifespan. Down here, these will live for trillions of years, literally. And that's my favorite, just because it throws in size. So you can see some of the really big ones are shown here, and then the small dwarf stars, the white dwarfs, which again is going to be our sun. White dwarfs are stars that no longer fuse the elements together. There's no nuclear fusion going on there. They're just going to take billions of years to cool off. They're done burning, and that's where our sun will end up. And again, it's not a physical location. This is just a graph that's just charting what it looks like, you know, the magnitude versus the surface temperature. The surface temperature is also the color. And the classification is O, B, A, F, G, K, M. Those are the classifications. When I was studying this, we use O, be a fine girl, kiss me to remember this way. You can use guy instead of girl if you like. It's still got a G, so that's very fortunate if you're looking to memorize that. All right, so let's look at the life cycle of a star like our sun. And they all start in a big cloud of dust. And the size of the cloud of dust that collapses is going to dictate how big a star is versus, in solar masses. And so our average star, which is our sun, is going to go through these stages: a red giant, a planetary nebula, and then a white dwarf. We're going to talk about that a little bit. And afterwards, we'll look at a massive star that becomes a red supergiant, actually goes supernova, which is a rather dramatic explosion. And then, depending on its initial size, will either become a neutron star or a black hole. Yeah, black holes are really weird, but we'll talk about that in a little bit. Okay, so all stars start out in a large cloud, as I said, at least a few light years across. And the life of the star is going to take different paths depending on how large a cloud has come into gravitational collapse. It takes millions of years for this dust cloud to collapse. But once it collapses enough and the gravity starts pushing it together, the gravity is going to heat up that gas. And it's going to keep heating up that gas until it squishes the atoms together and they start to fuse. So hydrogen atoms start to fuse and they ignite. The star actually ignites. And so then you have an outward pressure of the nuclear fusion pushing against the gravity. And at some point, the outward pressure of the nuclear fusion is going to balance out with the gravity, and it's going to come under what they call hydrostatic equilibrium. It just means that the star is now pretty equalized, and for our sun, that means like 9+ billion years. It's just going to stay on the main sequence, about the same size. It might differ a little bit, but it's going to stay about the same size. And but you need enough gravity so that you overcome the protons in the nucleus want to push against each other, and you have to smush them together with gravity enough that the strong nuclear force takes place, and that's when you get the fusion. So the nuclear fusion produces the outward pressure and pushes against the gravity, and then we have a stable star. And in this case, we have a red or a yellow sequence star born because of the, we're talking a star that comes out to be between 1 and 8 times the mass of the sun. I'm going to be talking mainly about something that's twice the mass of the sun. So that's hydrostatic equilibrium. You've got the radiation from the fusion is pushing out and the gravity is pushing in, and when that equalizes, we've got a star that has gone past the protostar stage into a steady state star. Once it burns through all of its hydrogen, uh, it starts to expand because for a while the force of the fusion gets less, and the star starts to expand, and the shell starts to expand a bit, and then finally it ignites the helium and starts to burn hotter, and the star comes back. So it becomes a red giant for a while, then collapses a little bit, and then continues to burn. Finally, once the helium's burned and it's created some carbon and some oxygen, there's no longer enough fuel or heat for it to burn any further, and the shell just kind of expands away from the star and becomes a planetary nebula. A planetary nebula has nothing to do with a planet. It's just that it's a fuzzy blob in the sky that looks the size of a planet. And so when astronomers in the 18th and 19th century were looking at it, they named it planetary nebula because it was a little round blob, and it was different than the planets, but it was different than the comets, and they were really looking for comets. That was really what caused them to catalog these planetary nebula. The planetary nebula, which is up to about half of the mass of the star, will stay and be illuminated by that star for about 20 or 30,000 years, and then it kind of blows off. And what's left behind is a white dwarf, which is a dead star that's no longer has any nuclear reactions, any nuclear fusion. It's just cooling off, but it'll take billions of years. But the planetary nebula that are left behind are very cool looking. This is just a diagram of the sun as it becomes a subgiant, a red giant. Then the helium burning kicks in, and after it burns through its helium, it becomes a red giant again, blows off its shell, becomes a white dwarf, which on this diagram moves down here into the white dwarfs, and the planetary nebula remains. They can be very beautiful because they're illuminated by the radiation of the star. It ionizes the gas in that cloud, which is really encircles it, but we often see it as a ring. This just shows the last stage of a star like ours, where carbon and oxygen has gathered in the core, and that's just before it burns itself out. This is called the Ring Nebula, and it's about 1,600 light years away from us in the constellation Lyra. On clear days in the summer, you can look straight up and you can see the constellation, and we show this often. It looks like a smoke ring when you look at it in a telescope, a really tiny smoke ring that doesn't have color. But you can see the white dwarf, about 15th magnitude, is sitting here. That's the star that blew off this shell. And the white dwarf is very high density. It's about a metric ton per cubic centimeter. So if you took a teaspoon of it, there's no way you're going to lift it. It's like as heavy as Mount Everest, just about. So it's a very heavy, very densely packed star. It has about half of the mass of the sun packed into the space of the Earth. White dwarfs are about the size of Earth. So, imagine the sun is 166,000 times the mass of Earth. So imagine half of that packed into the size of the Earth. It's just super dense. The different colors show different elements. The blue color represents helium. The cyan is hydrogen, and the oxygen is the reddish color. This ring is about 1 light year wide. So that means it takes light 1 year to travel from here to there. So that's a pretty large object. It's small in comparison to other objects in the universe, but still a light year away light year wide is amazing. The light from the sun takes 8 minutes to get here. So imagine how far it's going to go in 1 year, and that's the size of this ring nebula. Now remember, I spoke about different wavelengths outside of the visible wavelength, like infrared. So we have a picture of this taken in the infrared from the Subaru telescope, which is on Mount Haleakala in Hawaii, and they added that to this visible light picture. And we get this. This is what we were just looking at. That's the visible light. This is all picked up in infrared. It's from the heat, and that heat is from the star's red giant phase, when it became really big before it blew off its shell. So about 10,000, between 10,000 and 100,000 years before it blew off its shell and created a white dwarf, we have this heat signature remnant that we can still pick up with an infrared telescope. And again, it actually combines 3 telescopes: the Hubble telescope, the Large Binocular Telescope, which is earthbound, and the Subaru telescope, which is earthbound. Here's another planetary nebula. Again, we've got the white dwarf in the middle. This has more of a bipolar look to it, the way it blew off its shell. But that's about 1,200 light years away from us, and it was first discovered by Charles Messier in 1764. Messier put together a catalog of objects because he was a comet hunter. And so other fuzzy objects that were not a comet, he was interested in cataloging. So when he looked at the night sky, he would have it in his catalog, and he would move on to another object that might look like a comet. That's about the time when these were called planetary nebula. So there's the Messier numbers number a lot of the brightest objects in the sky that are not stars, and that astronomers still use that catalog, as well as others. This is an amazingly beautiful astrophysicists still don't understand how this was formed. It was formed by a star that was very close to our sun's mass, and it's revealed in this amazing detail by the Hubble Space Telescope. And what's really intriguing about this is, if you look, you'll see there's 11 rings around it. And those rings are really bubbles around the star. We're looking at it like if we had cut an onion, and then we look at the rings of the onion. But those are bubbles that surround the star. And you know, we've had this information for decades now, but we're still not sure how this was formed. The star may have ejected a series of pulses at 1,500-year intervals. There may be some magnetic companion that we can't see that was causing this. We just don't know. There's a lot of theories, but it certainly creates a absolutely stunningly beautiful planetary nebula. Oh, what happened? Okay, and then this one has been nicknamed Hubble's spirograph. Again, it's just another beautiful remnant of a star that's about the size of our sun. This image was taken 25 years ago with the Hubble spacecraft, and its boring name is IC418. So if you look it up, IC418 is what you'll find on star maps. It glows like a multifaceted jewel, and it lies about 2,000 light years from Earth. So one thing about astronomy is it's also time travel. When I say that this lies 2,000 light years away from us, what does that mean? Exactly. Yeah, we see this. That's how it looked 2,000 years ago. We won't know how it looks today for another 2,000 years. So that's why it's so important to our astronomers to look deeper and deeper, because when we look into a galaxy, and we've seen galaxies as old as 13 billion light years, we're looking back in time at what early galaxies looked at like near the beginning of time and space. And so the cosmologists who study galaxy formations are very interested in looking as far back as they can, because they're in a time machine looking back at time. And so 2,000 years is interesting, but when you go back 12, 13 billion years, that's where it gets really interesting, because now that we have the James Webb Space Telescope, up in the sky, it's giving us information that some of it we just can't explain about the expansion rate of the universe, and so there's a lot new problems for scientists to figure out. And also some of the stuff scientists thought they knew, now with the new data and with instrumentation to measure even more accurately, some of our theories are being turned on their head. And I'll be doing a talk on the James Webb Space Telescope in August if you're interested. But it's really, every time we send a new telescope up there, we learn stuff that we can't explain. And we get more information looking further back than we ever did before. It's very, very exciting. So all of these planetary nebulae I just showed you, they started out just like our sun. And after they burned through their hydrogen, they burned through the helium, carbon and oxygen started forming. The burning rate, it got cooler, and the shell just started to float away, and left behind the planetary nebula that we see here, and a white dwarf, which is a spent shell. So let's get an idea of the size of some of these stars. So that's not a star. Does anyone know what that is? Yeah, Jupiter, excellent. So I wanted to start in our solar system and start working our way up in size. Back in the 1990s, I think it was 1994, I might even have it in my notes, Comet Schumacher-Levy broke apart and hit Jupiter and left plumes on Jupiter. And this was a really exciting time for knuckleheads like me looking through the telescope. But we had to wait for Jupiter to rotate into view before we saw those. And the reason why I show you that is there's Jupiter. Those plumes that are on Jupiter are about the size of the Earth. So that kind of gives you a scale of the Earth. The Earth is about 7,900 miles in diameter. The moon's only 2,000. Jupiter's 86,000 in diameter. So 11 Earths can fit across Jupiter. And the sun is 864,000, right? So the sun is about 10 times the diameter of Jupiter, but about 1,000 Jupiters could fit inside the sun. All right, so that just gives you an idea based on Earth, Jupiter, and the sun. So let's see how the sun stacks up to some of our other stars. Well, there's the sun, and Sirius, Pollux, you see it's not looking all that big anymore. The diameter of Arcturus, which is a red giant, is about 21.96 million miles. If it was where our sun was, it'd be about 2/3 of the way to Mercury. So that's a pretty big star. And it's the brightest star in Bootes. Some stars have special names like Arcturus. Every star has a Greek name. So if you're the brightest star in a constellation, you get the Alpha. And then there's Beta. So Alpha Arcturus, Alpha Bootes is Arcturus because it's the brightest star in Bootes. And it's very easy to find. If you look at the Milky Way's got a handle that curves. So if you follow the arc, you'll find Arcturus. It's easy to remember. The first bright star you'll see, once you follow the arc of the Milky Way, the Big Dipper handle will be Arcturus. And then you speed on to Spica, which is another very bright star. I'm not sure how many light years away that is. That's a good question. I didn't put that down. Wow. Ninja. Here's Arcturus now. Next to a hot blue star called Rigel. Here's Betelgeuse. Has anybody heard of Betelgeuse? Besides the dude in the white and black stripes? Yep, Betelgeuse is the shoulder of Orion. So we had Orion all through the winter time. And it got a lot of publicity because people are predicting it's going to go supernova soon. But Betelgeuse is about the size that our sun's going to become, which is a little scary. Betelgeuse has a diameter of 765 miles, 765 million miles, and it's about 700 light years away from us, from Earth. If it was where our sun is, it would not only swallow up Earth, it would swallow up Mars too. And that's pretty much what's in the card. So if you were worried about the Andromeda galaxy colliding with the Milky Way galaxy in about 5 billion years, don't worry, we'll be safely inside a red giant like that right about the same time. Beautiful. 37 light years away from us is Arcturus. Thanks, Ken. You can fit 1.3 million Earths inside our sun, and you can fit 700 million suns inside of Betelgeuse. So our sun, right now, our sun is like 1 pixel on this screen. It looked pretty big for a while, but it's getting drowned out. Again, Betelgeuse being the brightest star in Orion is called Alpha Orionis. That's its star. It's the brightest star in the constellation Orion. It's also the 9th brightest star in our night sky, and it's part of the winter triangle, which is now fading away, and now the summer triangle is coming into view. So I hope you'll come up here throughout the summer and check out the summer triangle. Vega's there, and the that smoke ring we saw, the planetary nebula up there in Vega, will be visible all summer. So come on up, and we'll check it out. So the red supergiant Antares is about 604 light years from Earth. And it's 700 times the diameter of the sun. But the overall density is less than 1/millionth of the sun. You see, when a star becomes a red giant, the gas spreads out so thin that it becomes much less dense than when it was a new star sitting on the main sequence of the HR diagram. And Antares is the burning eye of the Scorpius, the scorpion. And it's beautiful. You can always see it in that direction in the summertime. It's a gorgeous star, and you can really see the red color. It's very apparent with the naked eye or through binoculars. Its exact size is uncertain, but it would have slightly more reach than Betelgeuse, and it's located about 5,000 light years from Earth. Finally, we've got VV Cephei. It's one of the largest known stars, and this changes because we keep discovering bigger stuff, especially now that the James Webb is up there. Its size is uncertain, but it's estimated as 1,050 to 1,900 solar radii. Its photosphere or outer shell would reach almost to Saturn, and it's about 5,000 light years from us. So we're constantly finding newer big stars. The biggest we know of right now, and I haven't even put it on this chart yet, is UY Scuti in the constellation Scutum, about 1,700 times larger than our sun. So there's always going to be a bigger guy on the street. That's the story. And while UY Scuti is the largest star, there's a star with a very boring name called R136A1. It's currently the heaviest star in the universe. It's located in the Large Magellanic Cloud, which you have to go to the southern hemisphere to see, but it's a naked eye object down from the southern hemisphere. It's about 165,000 light years away from us, and it's a member of a rare class of hypermassive stars weighing more than 170 times the mass of our sun. It's between 170 and 230. And then the title of the brightest star in the universe, in terms of intrinsic luminosity, absolute magnitude, goes to a variable star called Eta Carinae. And again, that is visible in the southern hemisphere. Eta Carinae outshines our own sun by over 1 million times. It's amazingly bright. And I was just in New Zealand in March, and I got to see these objects and actually photograph them. And I'll be talking about my trip to New Zealand in my smart telescope uh, talk on September 13th. I took a little smart telescope, $350 telescope that you could put in my briefcase, and it produced amazing pictures right on my smartphone. The advances in our technology have just become amazing. There's not even an eyepiece on this telescope. I just put it, I level it, and then I tell it what I want to look for, and it has a star catalog. It knows where it is. It looks for it, and it makes 20-second exposures, and then it stacks those exposures on top of each other. So I took like an hour of 20-second exposures, and the software stacked them all on top of each other and produced beautiful pictures of the objects that I was photographing. So if you want to learn more about that, September 13th, I'll have a whole bunch of different stuff. I'll even have a smart telescope here to look at. It's an inexpensive way to get into the hobby for sure. It's called a C-Star, by the way. C-Star, there's a 30 and a 50. Okay, so as we saw, there are some really big stars out there. Some of them are in their death throes, but others are just big because they were born big and massive. So what happens to them? Well, for stars greater than 8 times the size of the sun's mass, they won't experience a helium flash and then throw off their outer layer and then just whimper away into a white dwarf. They have a much more dramatic ending because they don't stop at carbon and oxygen as far as nuclear fusion. They go on. So just like low mass stars, they start with a collapsing cloud of gas, but a much larger cloud, of course, has formed them. And a higher mass star means more gravity, which means higher temperatures. And higher temperatures mean faster fusion. That's why they burn out quicker. That's why they die quickly. They don't last for 10 billion years. They last billions of years. They can burn through hydrogen in 100 million years or so. And this creates greater outward pressure to counter out the gravity and results in a larger star that is much brighter and therefore bluer in color. Stars up in that region, like here, these are the stars we're talking about. These large, they're the hottest stars, they're the bluest stars. And just like a low mass star, the high mass star burns through to the end of their hydrogen. They burn their hydrogen first, and then the star starts to grow in size again. But unlike small mass stars, nuclear fusion doesn't stop at carbon or oxygen. It keeps going. From oxygen, it starts to burn neon, and then it burns silicon. And each new element is taking a smaller area of the core and is burning for a lower amount of time. You know, for example, a large star may burn hydrogen for 100 million years, helium for 10 million years, carbon for 10,000 years, and so on. I'm just showing you an example there. But the star keeps burning until it comes to iron. Iron is the end of the road for any star, no matter how big it is, because the reason is that all of the elements up to iron produce energy, right? There's less mass than the reactants. But when you fuse iron, the product of iron fusion has more mass than the reactants. That means it needs energy rather than gives off energy. And as soon as iron builds up, here's a picture of a core of one of those large stars. As soon as iron builds up in the core of a high mass star, there's catastrophic consequences. The process of fusing iron requires the star's core to use more energy, which causes the core to cool. This causes outward pressure to go down, and so the gravity collapses it, it gets hotter, and it bounces a couple times, but finally, and this is just within a couple minutes of iron showing up on the scene, it bounces off the iron core, and we have a supernova explosion. This just shows the HR diagram, and the largest star is plotted coming across here. Uh, Again, we just, for a brief period of time, the amount of light generated by a supernova outshines an entire galaxy, of millions of stars, billions of stars in some cases. So one star generates uh, that much luminosity, about 1 billion stars like the sun. And these explosions are so bright, they're visible at immense distances. If one were to explode near us, we'd be able to see it in the daytime. And no one has been able to see that in modern times, but Tycho Brahe, an astronomer, saw that. We have records of Chinese and Japanese astronomers in the year 1054 saw the supernova that created the Crab Nebula, and they recorded a star that they could see in the daytime, and that was a supernova explosion. This is a Hubble telescope picture of the remnant of that same supernova, 1987A. This is pictures of the Hubble took of the shock wave from that 1987 supernova lighting up a debris field around the star. And you could see how over time, many years, it gets brighter and brighter as that ring gets energized. This is just an artist's conception of the shock wave coming out of a supernova. Supernova explosions leave behind a superdense core known as a neutron star, or a black hole if it's really big. Also, it's the supernovas that produce all the elements that are heavier than iron. So all of those elements are just produced either in a supernova explosion, or a collision between two black holes, or a collision between a black hole and a neutron star, which is why those elements are just so rare, because they're only created under very extreme conditions. So this is a picture, this is a artist rendition of a neutron star, which can have a mass greater than our sun, but only be about 12 miles across, like the city of New York is about 12 miles across. So imagine the mass of that's greater than our sun piled into an area the size of New York. And then the sun weighs about 333,000 times more than Earth. So imagine the mass of 166,000 Earths packed into the space the size of Manhattan. We're talking about a tiny star that's approximately 1 trillion times more dense than our sun. And if that's not enough, they spin around multiple times per second. So think of the island of Manhattan with half the mass of our sun spinning around. The fastest one has been clocked at 1,716 revolutions per second. It's just unimaginable, and throwing off relativistic jets of energy on both sides. Theoretically, their initial spin can be as fast as 1,000 to 1,500 revolutions per second. And again, this is an artist rendition of a isolated neutron star. There's not many actual isolated neutron stars. There's only about 7 out there. As a matter of fact, they were named the Magnificent Seven until they found the 8th one, and so they named it the 8th member, Calvera, which is the bad guy in that movie. Here's an example. This is the Crab Nebula. This is the remnant of that supernova that the Japanese and Chinese astronomers recorded in the year 1054. So that's what it looks like today. It's called the Crab Nebula. It's got a Messier catalog number of M1. It's the first one that Charles Messier entered. This is a mosaic image taken by the Hubble Space Telescope. And it's 6 light years wide. So the light takes 6 years to get from one side to the other. And again, the neutron star in the center, like a lighthouse, ejects twin jets of energy. That's why they're nicknamed pulsars, because they spin along quickly emit energy, and it looks like they're pulsing, just like a lighthouse looks like it's pulsing when the light spins around. This is another image of the Crab Nebula taken from 3 different spectrums. It's the Hubble Space Telescope is purple, the X-ray light from the Chandra X-ray telescope, which is in blue, and then infrared light from the Spitzer Space Telescope is in red. So that is a totally different view of the Crab Nebula by adding other wavelengths. Some neutron stars emit radio waves in the form of radiation, and because they spin so quickly, they can look like little stellar lighthouses. This is an artist's rendition of another common neutron star configuration, where there's a neutron star and he's preying on a companion star or a binary star. That was interesting. And then finally, on the bottom, if you're over 60 or 80 solar masses, you're not left with a neutron star, but you're left with a black hole. And that's an artist's rendition of a black hole. Black hole is so dense that even light cannot escape from it, and it bends space-time. This is the closest we have to a picture of a black hole, and because light can't escape from a black hole, what we're actually doing is we are photographing the accretion disk. As the black hole gobbles up matter around it and it falls into the black hole, the matter heats up and starts spinning around as it falls into the black hole. So we're not actually photographing the black hole, we're photographing the matter that it's about to gobble up, and that itself will disappear. This was taken very recently, 2017, I believe, it was released. If you compress the sun down to the same density as a black hole, it would be 6 kilometers in diameter, very small. And remember, the sun is actually 1.4 kilometers across now, so it would go from 1.4 kilometers to 6 kilometers. 1.4 million, sorry, 1.4 million kilometers down to 6 million. And that's the home of that black hole that we've actually gotten a picture of. It's called the galaxy M87, about 55 million light years from Earth. And it's an elliptical galaxy. Another thing black holes do that have really been a boon to science is, since they bend space-time, if you have a massive group of galaxies with black holes, they bend space-time so much that galaxies directly behind them are magnified but distorted. And so you'd have like this lensing device is about 5 billion light years from us, and the galaxy that was magnified is 10 billion light years behind it. Just amazing. So we can point our instruments towards these supermassive areas and see this lensing effect. And even though it's very distorted, we can learn an awful lot about what's in those galaxies. This one was an amazing picture. Einstein predicted that if something went supernova behind a gravitational lens, that we should be able to see across. And it was decades later that we actually filmed what's known as an Einstein cross. This supermassive galaxy with a black hole in it has bent space-time so much that a supernova went off behind it, and we got a picture of that supernova taking 4 different light paths around the lens. Just amazing. And we've seen that in a quasar as well. A supermassive quasar also warped space-time such that a supernova behind it made a cross, and the slightly different paths, so slightly different times within that supernova that we're looking at. And finally, I'll leave you with one last one. It's called Gravity Grin. Gravity's Grin. It's again, it's a two supermassive galaxies interacting, bend space-time, and it curved the light from galaxies behind it such that it frames a little face and a smile there. I usually save that just for my Halloween presentation, but there it is. It's Gravity's Grin, and thank you very much for coming tonight.
All right. Thank you, Walt, for another great presentation. So we are going to have a question and answer session because I do know a number of people online had questions, so chances are you also have questions. Just a reminder, if you need to use the bathroom, that is the porta potty in the back. To my left, your right, we have a museum and gift shop area. I'll be manning after the question and answer session. We do have occasional holes in the clouds, so things are looking up.
I won't feel insulted if you go look at the telescopes, believe me.
Just a reminder, when we do go to leave, we are using our headlights and flashlights. We keep those pointed towards the ground. For people here who want to ask questions, you're going to raise your hand and kind of wave it about. I'm like a T-Rex, so if you stop moving or put your hand down, you cease to exist in the darkness of the night. Online people, you have a DC, you just get to type. Such as life is. I'm going to start off with our first online question is, where does the new color science found fall on the electromagnetic spectrum?
The new color found?
Apparently, science found a new color. This is
I would be making up an answer.
I vaguely recall there being an article that I did not read.
If it's a color that we can see, it's got to be in that visible light spectrum because we can't see into infrared, we can't see into ultraviolet. So it has to be in that narrow range, but that's all I know. I don't know. There are so many colors. I mean, Crayola creates new colors every year. So I'm not really sure what
I mean, we
is.
also have
I'll have to look that up.
The fun art people who do the things like the black is black and the pink is pink and the blue is blue. So there's always new color stuff happening.
Absolutely. My grandkids come up with new ones all the time.
And
unfortunately, they're on the walls of our kitchen, but
I think now they're also saying some people are starting to be born with an extra type of, is it rod or cone, the color sensing ones, so they can see more. So anything's possible. Was there a question out here? Or are we just pointing at things? Yes, Jupiter is out. Honestly, we heard someone here super excited, and I love to hear, "Mom, quick, come, it's Jupiter!"
I love it. That's great.
Before the clouds hit it again. And it was honestly the cutest, most, it honestly made my night, hearing that. So our next online question is, there was a lot of chat. We were talking about things like paleontology or archaeology and whatnot in chat. What is happening behind? And they never answered behind what. But if you're, for the online people, if you're talking about what's happening behind the speaker, it's just the presentation you get to see rear projected for people here to be able to see, because people here don't have fancy screens that they get to see it on unless they pull up the Twitch or YouTube.
And we do have some moths hanging out.
Yeah, there's always a moth party when the light gets when it's dark and there's light of loud. Questions? Like I said, if you have a question, raise your hand. I will see it. There was a comment that this looks like a print you can get from the NASA website. I did answer that, as I think that's one of the sites you pull from for reference images.
All the images that are on here, unless I say I took them, which is going to be my smart telescope. But today, it was all public domain. I take it off university websites, JPL, NASA, the Hubble website. It's all stuff that we've paid for through our taxes and is free for the taking. But you can also see every slide I give credit to where I get those pictures. Because the people who do the hard work should get credit for them. But it's all public domain. Well, I won't say public domain because some's copyrighted and you have to note it. But it's all stuff that you can get on the internet. Absolutely. Which
Right.
means you should go look on the internet instead of YouTubing vegetational stuff. Look for some educational stuff. It's all over there.
Yeah, and NASA is actually a good place to pull this reference material from because they're less likely to be using robots to create these images. All right, so our next online question is relativistic jets. Is that also known as shrapnel as the forces tear it apart?
I guess you could think of it that way. It's called relativistic jets because it's shooting out these hot gases and neutrinos at speeds that approach a fraction of the speed of light. And since they're coming out so quickly that you could measure them against the speed of light, they're called relativistic jets.
Neat. I did not know that. And people online, if you have any last minute questions, do get those in. I want to tell you now because stream delay is a thing, and by the time you hear this, we're already 2 minutes into the future. Speaking of relativity, just quick checking and questions. Bueller, we don't. It's cold and windy enough. We don't even have the crickets this time.
Yeah.
All right. It looks like one of our last questions is: do we theorize that there are any life cycle steps that after the ones you showed on the graphic? So, like, I believe that was the something, the neutron star, the black hole.
Yeah, I mean, if it's life cycle, then on the other side of death is really just the cooling down. Right, a white dwarf, after billions of years, will turn into a black dwarf when it totally cools down. They would be hard to see even now because if they're black, they're going to be very hard to find. But also, it takes so long, and the Earth is, the universe is thought to be just under 14 billion years old. So if something takes billions and billions of years to cool off, those objects haven't even been formed yet because none of them have had enough time to cool off. That's still billions of years in the future. But that would be the end game for that. Neutron stars slow down slightly. Stephen Hawking tells us that black holes evaporate very slowly. So in some amazingly huge time frame, you will have black holes evaporating. That would be the very end stage. The universe hasn't been around long enough for us to see any of it.
Does black holes, and this is my own, does black holes evaporating have any weird consequences with the whole conservation of matter and energy law thing? Because
I don't know. The second law of thermodynamics tells us that things, that energy degrades into unusable energy. The amount of energy stays the same, but it turns into unusable energy, and the amount of chaos in a system increases. So it pretty much follows
chaos.
the laws of thermodynamics.
But yeah. Anyhow, it does look like that's the end of our online questions. Like I said, thank you, Walt. Thank you,
Thank you. Thanks for
everyone
hanging in
here
there.
and everyone online for joining us. Do check us out on our website, uacnj.org, and our socials, our Facebook, our Instagram, and our Discord. You'll be able to see any upcoming events and fun things that we post.
And do check out Jupiter and whatever else is out there. You'll see any shed with the roof rolled off it has an active telescope. So you can just walk down the street and you'll see one or two on the left. There's usually one in the back right that's up and running if there's enough to be seen. But
Alright.
yeah, step
And
right up and take a look.
With that, everyone have a great night, clearer skies than we have, and good seeing.